In this video, we're going to continue our conversation on air conditioning troubleshooting, and we're going to troubleshoot some basic air side problems. Okay, and this is common issues. There's way more beyond this, but let's start off with the common ones for this video. Airflow issues have the potential to cause elevated humidity in the conditioned space, which in turn causes mold, improper cooling and occupant discomfort, air quality issues, lack of ventilation. It can also cause frozen coils, which in turn can cause water damage and compressor failure. It's important to look at airside issues for obvious signs of airflow on each and every service call. There's way too many technicians who are looking at that outside unit, a motor, a control board, but do not check the airflow, okay? And we really need to do that, okay? So let's talk about some of the inspection and testing procedures. You want to start by looking at the simple things. You have to solve these problems as you go. For example, is the filter clean? If the filter's dirty, everything else you do will not mean or resolve anything. So start off, is the filter dirty? This is an example of a dirty filter. Okay, this filter caused over $25,000 worth of damage in a home. Okay, so just keep this stuff in mind. If a filter's getting sucked in to the point where the pleats aren't even visible anymore or barely visible, we need to change the filter. Okay, because you can't diagnose anything else. You cannot check anything further on the equipment before you change this filter. Open the air handler and look at the blower wheel. Is it dirty? A dirty blower wheel will not move the correct amount of air. Dust and dirt buildup on the blower wheel will fill the scoops of the squirrel cage wheel and not allow it to catch the air. Clean a dirty blower wheel before moving forward. In most cases, a mildly dirty wheel can be cleaned with a brush and a vacuum in the unit. In the case of extremely dirty, crusted on dirt, or if it's been wet, the entire blower assembly may need to be removed to be cleaned outside with a more thorough cleaning, sometimes involving a hose and soap. So again, do what you can before you move forward with the testing, because a lot of these things, filter, blower wheel, will solve your entire airflow issue. This is an example of a sort of nasty blower wheel. If you take a look at all of the buildup on the wheel on this is barely moving any air. Okay, and by the way, this was not the same air handler that filter came out of. Two different air handlers. Notice that it's just caked on here. While you have the filter out, if you're able to, take a look at the inlet side of the coil. 9 out of 10 times that filter is going to be sitting next to the coil or under the coil. Okay. Some dust and dirt is expected, but if it's caked or if the fins are severely damaged, this will also impede airflow. The cleaner the coil fins are, the better the heat exchange, the better the air will move through it. Severely restricted and dirty coils need to be pulled and be cleaned. In most cases, this involves a few hours of work and great expense. If the coil's just dusty or has a few bent fins, you may be able to clean it with a vacuum cleaner or some coil cleaner. Be careful on the type of coil cleaner you use on aluminum coils. Some of the harsher cleaners will dissolve the aluminum and cause leaks. Also make sure that your customer does not have allergies to any chemicals if you're cleaning in place, because you can't rinse off all the dirt, all the chemicals you used out of these systems if you're cleaning in place. People have chemical allergies, specifically to chlorine and some of the other sulfur-based chemicals, and you just got to be aware. This is an example. This is looking up through where there was a filter. You can actually see a piece of the filter on the side. We're looking up at the bottom of an A coil. You'll notice over here, there's dirt buildup. There's fin damage. There's only really a little bit of relatively, and I'm saying that relatively clean coil here. Very little air is moving through the system. Okay, so again, this is a situation where this coil is dirty enough that it's not going to give good heat exchange. You're not going to have good airflow, and it eventually needs to be pulled and cleaned. Once your initial visual inspection and cleaning is complete, you need to put the system to cooling mode, fan on, and wait 10 minutes after the start of the compressor. Then using your thermometers and static pressure gauges, take supply air temp, return air temp, supply air static pressure, return air static pressure. And by the way, supply air temp and return air temp, you want both the dry bulb and the wet bulb. Also take the amperage of the blower motor. Now, it's good practice to take this amperage with the equipment cover on. So in some cases, you do need to be creative. If you must take the amperage with the blower compartment open, do it before you take your temps and static pressures, and then put the covers back on and wait for stabilization. If taking the amperage with the covers off, your amperage will be a little greater than when the covers are in place. If you have a ECM motor, you must take your amperage readings with the blower compartment covered. The easiest way to do this is to take it at the disconnect or wiring connection outside the unit. You cannot, with an ECM motor, you cannot achieve proper amperage and proper rotation and proper speed on that motor unless the motor's running at its normal condition, and that's with the covers on. So what we hope to gain out of this is we have a temperature split. Okay, you have your supply air temperature, in this case return air temperature, in this case 61.8. Supply air temperature, in this case, is 50.8. Delta T is 11. Okay, that's the difference between the supply and return temperatures. Most temperature splits are closer to 15 degrees between the supply and return. However, without looking at humidity and wet bulb and comparing with a chart, you cannot see if your temperature split is good or bad. Okay, the days of just using dry bulb temperatures for temperature splits are over. The systems today are more complex than that, and humidity plays a great role in our temperature splits. So, some of our tools, this happens to be the Testo Smart Probe tools, allow us to do a good cooling load evaluation. You'll notice we not only have return air temps in the dry bulb, we have return air temp wet bulb, supply air temp dry bulb, supply air bulb temp wet bulb. Okay, we also have our relative humidities of supply and return. Okay, and then we have our volume flow. This comes from the size of the system, and this calculates out to see how much cooling is actually being produced by the system. Okay, so let's take a look at these numbers, and I'll flip back to the slide in a minute. This is a 2.5 ton system. The required airflow for the system is 1,000 cubic feet per minute, 1,000 CFM. Each ton of cooling requires 400 CFM of air, so 2.5 times 400 is 1,000. Based on the temperature split, the required airflow, and the wet bulb temperatures, this system is only delivering 15,559 BTUs per hour of cooling. A 2.5 ton system is rated at 30,000 BTU per cooling. So based on the temperature splits, the humidities, the required airflow, and the wet bulb temperatures, this system is only delivering 15,559 BTUs per hour of cooling. A 2.5 ton system is rated at 30,000 BTUs. A 1.5 system is rated at 18,000 BTUs. So the important point here, and what you're getting from the airflow numbers, is the system in this example is providing 12,000 BTU per hour, or 1 ton less cooling than it's designed for. The challenge here is to find out why. Okay, there's a lot of extra money being wasted on this system because it's not providing the cooling it's supposed to be providing. So again, we can get that from using the proper tools and using the proper readings. Now, granted, what I have here is giving us more information faster, okay? But you can do the same things by using a chart. Okay, the next thing we want to do is take our return and supply static pressures. Okay, when you're looking at static pressures, you want to drop the signs and add both numbers together to get the total external static pressure. So in this case, I have a negative 0.92 inch return static pressure. So we're going to take 0.92. We're going to add our 0.57 supply static pressure, and I'm going to come up with a 1.49 inch water column. Okay, that's our standard for static pressure readings. Okay, it's just a pressure in the ductwork. So the number we need to use is 1.49 in this case. In this case, we're going to drop the signs, add both numbers together for total external static pressure. 0.16, 0.81 is 0.96. Then you want to compare your total external static pressure to the static pressure on the data plate. In most residential air handlers, the total external static pressure should not be over 0.5 inch water column. That's what the systems are tested and designed for. In both of our static pressures above that I showed you on the prior slides, we have airflow issues. This will prevent proper cooling and can actually damage equipment. Okay, and I just want to, on this one, this is a part of a data plate. I lopped the serial number off just because of privacy issues. But tested the external static pressure is rated at 0.5 inches water column. So anything above and below that, okay, below I'm okay with because it just means we have really great ductwork. But above that, we just need to be careful, okay? Because there's a ductwork issue, there's an airflow issue someplace. Now, a static pressure that's too high on the return side can actually suck the condensate right out of the pan. Okay, so a high static pressure can actually cause a flood with condensate being pulled off the coil and out of the pan. So you got to be very aware of static pressures, and not taking them is a problem. The next thing you want to do is we want to inspect the ductwork. If you have static pressures, if you have any static pressure concerns, the next step is to do a visual inspection of the ductwork. Most often you can spot the problem visually and resolve. Let's look at a couple examples here. What's our problem here? Okay, this system had an extremely high return static pressure. It's not the same one that I just showed you the readings of, but it's a good example. Okay, high return static pressure. Same system here. Okay, high return static pressure. That's a return box right there. Well, kinked flex ducts are the biggest cause of static pressure issues. Flex lines should be straight, and if not straight, they should have loose turns, they should be pulled tight, and they should never have sharp bends. Flex lines should also be used in the shortest distance possible. Okay, so right here, I have a 180-degree bend on a flex line. That's a problem. I also have a strapping here that's actually helping compress this whole situation. On this one, someone decided that the right way to run the flex line was to shove it between the joist structure and the attic. Again, here, this is all compressed in the center here. Not a good thing. Okay. Another picture here. Okay, notice on this return box, we have water, or this is a supply plenum, we have water dripping down. Okay, where there is moisture, there is duct leakage or problems with the insulation. This is in a humid attic in Florida. Okay, where we have moisture, there are leakage issues. Connections should be tight. Signs of moisture means duct leakage or insulation problems. Where there's moisture, you must do a closer inspection. Moisture on or in ductboard means that that section of ductboard will need to be replaced. Moisture causes ductboard to break down. Here's another example. This happens to be on the return side of the system. Take a look at the big gap where the ductwork was not properly connected. The flex duct, which runs around there, and there's even more issues here because you'll see that this is all compressed here. It wasn't cut proper to the length. But you have a big gap right here. Okay, this flex duct was not properly connected to the return plenum. This is right at the air handler. Okay. Another picture of another system. Again, you'll see all the duct tape is falling off here. These are no longer properly sealed. Duct leakage in unconditioned spaces is a serious problem. Duct leakage on the return side pulls unconditioned, humid, and polluted air into the system. Think about the air in an attic, especially in an older house, especially in a house that might have bats or squirrels or mice living in the attic. Duct leakage on a supply duct will force air out of the ductwork into the unconditioned space, lowering the effective cooling, but also depressurizing the building, which causes a host of other problems. Duct leakage must always be fixed. You cannot avoid fixing duct leakage, and it is so easy to identify. This is an example of duct leakage. Okay, dust that has blown out of a supply register along the ceiling. Okay, there's duct leakage here. It's actually on the return side. It's pulling air in from the attic, and the filters be in the house, so the return air is actually pulling the attic air in after the filter. So once you've checked all for visible airflow issues, you have to finalize everything. Once you fix the issues, go back and retest everything. Record your before and after readings. Okay, this is very important because you should be able to show your customer a change. You want to make recommendation for things that you cannot fix on the spot, as well as permanent repair of any temporary repairs you have made. Okay, if you've gone through and sealed a return duct with duct tape just to solve the problem immediately for the customer, sooner or later someone's going to have to go make a permanent fix on this. Okay, duct tape is not the answer to everything. Okay, if you find missing ductwork and you're able to seal it up a little bit, still somebody has to go through and make the change. If you find wet ductboard or wet insulation on sheet metal ductwork, you still have to make a recommendation for permanent repairs. You cannot leave wet ductwork forever. It's going to fall apart and it's going to cause mold. Okay. So once that's done, you've done actually a good job for your customer or for your own home in finding the issues. We still have a lot more to talk about with airflow issues because they're part of the biggest problem people run into and miss in air conditioning.